Okay, so it's a great pleasure to have Masaki Oshikawa with us here at this workshop, who I believe came all the way from Japan. So thank you very much. So Masaki will talk about flux quench in interacting spinless fermions in one dimension.
Thank you. So I'd like to thank the organizers for kind invitation. I'm happy to be back at Newton Institute. First time I came here was I think 16 years ago or something, year 2000. There was a workshop on strongly correlated electron organized by Alexei Tverik, so that was fun. And yeah, this time, yeah, same institute, you got new building, but most notable improvement about this institute is food in the cafeteria next door. The last time it was terrible, I have to say, but this time it was quite good. So there is.
Is
Yeah.
it still the same bicycle as 16 years ago?
No, I bought this maybe 7-8 years ago, so I didn't have this one last time, but okay. So now I'm carrying around. So today I like to talk about one particular problem of quantum quench in integrable system, but I'm going to report mostly numerical result. Actually, I hope that we could understand better about the result using the integrability and so on, but so far we don't have much mathematical insight, so maybe mathematical aspect is so far largely lacking. But I'm giving a talk on this here partly because there are so many experts in the audience. Hopefully some of you have better idea how to understand our numerical result. Okay. So my talk is based on a paper collaboration which appeared recently in arXiv with a student of mine, Yuya Nakagawa, and also Gregor Mizgish in Sakurai. Okay, so first introduction, but I guess I don't need to give any introduction why quantum quench is interesting and integrality, blah, blah, blah. You already know much about this. So I skip this introduction part and just define the program, which is simple. So maybe I should say XXZ model, but of course you can do Jordan-Wigner transformation to map the system to spinless fermion problem is density interaction between nearest neighbors. But probably you are more familiar with this XXZ model. So we consider this XXZ chain, which is of course integrable. And then we introduce some kind of twist, or in particle language, this can be interpreted as vector potential. So you can introduce this vector potential either in...
Actually, it's a Zelashensky-Maria interaction.
Oh yeah, in spin language, yeah, right. So so vector potential is more like this in particle language. Yeah, you can write this in terms of Zelashensky-Maria. Yes, thank you. Okay, then we can introduce this twist term. And then, okay, so first, without the twist, of course, you know phase diagram very well, but just to fix the notation. So in my talk, delta is defined such that positive delta corresponds to ferromagnetic XXZ. So for delta bigger than 1, in spin language, you enter ferromagnetic, Ising-like easy axis ferromagnetic. So the ground state in particle language is either completely empty or completely filled. And for delta negative is anti-ferromagnetic or repulsive interaction regime. And for delta smaller than -1, you enter nail phase in spin language or Mott insulating phase in particle language. And in between, between -1 and 1, you have gapless critical phase. Low energy limit of which can be described by Tomonaga-Rattin-Jargit. And in particular, delta equals 0 corresponds to XY chain or equivalently free fermion model. And so I just introduced vector potential or Zelashensky-Maria. Then if you impose a periodic boundary condition, then this phase theta at each link corresponds to some magnetic flux piercing through this link. So the total flux inside this ring is given by theta times n, where n is the number of sites, if you consider a finite size system. So the problem we want to consider is sometimes called flux quench, because it corresponds to sudden switching off of this flux. So let's say before quench, for T negative, the system was in the ground state, let's say for some non-zero theta. And at T equals 0, I suddenly switch off this flux. So post-quench, that is T greater than 0, I just do time revolution with respect to post-quench Hamiltonian, which does not have any flux, theta equals 0. So this is a problem. So this sudden switching of the flux means that you just switch off vector potential at T equals 0. So that means that you generate basically delta function like pulse of electric field. So you just apply electric field only at T equals 0 with the delta function pulse. And the amplitude of this delta function pulse is given by this theta before quench. So this is a problem, and so there is interesting or useful property of this system. Although so far we couldn't have utilized this property too much for this quench problem, but nevertheless this is kind of exact symmetry of the system. That is, for this kind of flux problem, there is a gauge invariance, or more precisely, there is a large gauge invariance. That is, if you have flux inside a ring, which is integral multiple of unit flux quantum. In our convention, unit flux quantum is just 2 pi. So if the total flux phi is 2 pi times some integer, then basically particles do not touch directly this magnetic flux. So it's only the so-called Aharonov-Bohm effect that's how magnetic flux affects the system through the vector potential. But as you know, if you have integral multiple of unit flux quantum inside a ring, then basically there is no Aharonov-Bohm effect. So that means that for this kind of flux, the Hamiltonian with flux must be equivalent to Hamiltonian without any flux. But if you write down the Hamiltonian, this side has vector potential, non-vanishing vector potential, but this side has zero vector potential. So obviously Hamiltonians are different. But equivalence means that they are connected by some unitary transformation, which is gauge transformation. But this gauge transformation actually winds a phase in non-trivial way. So this is called large gauge transformation. And probably many of you are familiar with this Lipschutz-Matisse theorem and so on. And this large gauge transformation operator is nothing but what appears in Lipschutz-Matisse theorem as a twist operator. So anyway, if you apply this gauge transformation, you can map Hamiltonian with zero flux to Hamiltonian with some integer times unit flux quantum inside a ring. So this is useful because if you know the exact ground state of H0, that is Hamiltonian without any flux, you can easily, at least formally, give exact ground state for the Hamiltonian with flux. So it's just if you have ground state for zero flux, you just apply this twist operator then. Yeah.
One question. So if you have periodic boundary condition, what is the meaning of that J?
J, oh yeah, so J runs from 1 to n.
So something is happening at J.
Yeah, so only if this coefficient is 2 pi times some integer, then yeah, phase comes back to 2 pi times integer. So for fractional value of flux, this doesn't work for periodic boundary. But yeah, that's the point. So once you know the exact ground state for zero flux, you can also know exact ground state for this value of flux. But so this is just a relation between finite flux Hamiltonian to zero flux Hamiltonian. But of course, the quench dynamics can be non-trivial because initially pre-quench you have this ground state. And the post-quench, this is no longer ground state. So it has some non-trivial time evolution. So that's how we find the non-trivial quench problem. So as I said, so this is exact property, but so far we couldn't have really utilized this property to understand the quench problem. So, but maybe in some way this can be utilized. Okay, so if you apply this large gauge transformation to fermion annihilation operator with particular momentum k, so C tilde k is a fermion annihilation operator with momentum k, then this can be easily shown to be just another fermion annihilation operator with shifted momentum. So basically this twist operator or gauge transformation, large gauge transformation, just shifts the momentum of fermions. So for example, if we draw the momentum distribution function in the ground state, so this red dots are the momentum distribution function in the ground state of some XXZ chain. I forgot the interaction parameter. This shouldn't be free fermion with some interaction. Sorry, I forgot to write. But anyway, so it has some non-trivial shape because of the interaction. But if you add non-zero theta, this vector potential flux, then momentum distribution function in the ground state under the flux is just shifted to the right because of this relation. So at least in terms of momentum distribution, if you know the momentum distribution for zero flux, for finite flux ground state, you just shift the entire momentum distribution to the right. Okay. Then, so we can measure many different quantities in principle, but probably of particular interest is current operator. So intuitively, as I said, this flux quench corresponds to application of delta function like pulse of electric field. So you accelerate particles at t equals 0. So you expect some current to flow. And in fact, we will find some non-vanishing current after the quench. So current operator is, as usual, defined like this, so that it satisfies this continuity equation. And because in this problem, everything is translation invariant, so vector potential is introduced in uniform way. There is no particular special site. Every site is equivalent. So it's natural to consider the uniform component of the current. That is just the average of all the current operator. Is given like this. And in momentum representation, it's just a momentum occupation number for each momentum times sine k. Then you sum over all momentum k. So this is a uniform component of the current. And so because, as I said, in the initial state, you are in the ground state with respect to the Hamiltonian with non-zero flux. So the momentum distribution function is shifted. So there is some asymmetry. So at t equals 0, the expectation value of current is non-zero. Sorry, I forgot to say that, of course, in the presence of vector potential, this should be modified. You need to introduce vector potential here. But this is current operator for post-quench Hamiltonian without any vector potential. So in this problem, the initial state is given by ground state of Hamiltonian with flux, which is equivalent to the ground state of Hamiltonian with zero flux. Then you shift the momentum. So you can see that the expectation value of this one should be non-zero in the initial state. Okay. Then I do this time evolution with respect to the post-quench Hamiltonian without any flux. And if you consider equation of motion of this uniform part of the current J, then it's given by commutator between J and Hamiltonian, of course. Then this commutator is basically proportional to delta times, this delta is interaction parameter or anisotropy parameter of XSC, delta times some operator. So this is some non-trivial operator, but one point is that if delta equals 0, if the system is non-interacting, then this right-hand side vanishes. So that means J is conserved. So for free fermion model or equivalently XY chain, once you give the initial state that gives non-zero expectation value for J, then it never changes for free fermion point. But in general, if delta is non-zero, the commutator is non-zero, so the current expectation value shows some non-trivial evolution. That's what we are interested in. Although for delta bigger than 1, you have ferromagnetic ground state that is completely empty or completely filled. So that state is also insensitive to any flux. So we have non-trivial evolution of the current only for delta smaller than 1 and also except delta equals 0. Okay, and as I said in the beginning, of course, in this gapless phase, which is probably most interesting, the low energy effective theory is given by so-called Tomonaru-Rattinger-Likit, which is nothing but the field theory of free bosons in 1+1D. But if you just consider this free boson Lagrangian or ideal Tomonaru-Rattinger-Likit, then current operator, so local current is given by some derivative of phi. So if you consider the uniform component of current, this capital J, so you integrate over this derivative of phi. So J corresponds to difference between the boson fields at boundaries, the right end and left end. Okay, so if you impose periodic boundary condition, you might think this vanishes, but because phi has some periodicity, you can have non-zero value of phi as long as this difference is multiple of some unit that is allowed even under periodic boundary condition, and that gives you the uniform component of the current. So if you consider just this Lagrangian, this is again completely conserved. So in this description, the current operator, total current operator is conserved everywhere in gapless phase. But this is actually not really true if you go back to the microscopic model, because if you really try to describe the original microscopic model XXZ chain phase-free, then you must have some perturbation to this free boson Lagrangian. And those are irrelevant in RG sense. So in true low energy limit, you can forget about those irrelevant interactions. But if you are interested in finite time dynamics, then you need to include irrelevant operators, which we haven't really done that. But
if you go back to the previous slide, I remember everything depends on difference on point, no? So you might think that this is some kind of double derivative or something. First derivative and another, so this gives you already a dimension 2 plus something that probably indeed is the operator you're looking for.
Yeah, so if you do dimensional analysis and so on, I think in continuum limit, this corresponds to some irrelevant operators.
If I understand correctly, so you're saying that for free fermions you can't induce any current, or what?
Pardon me?
For free fermions you can't induce any current in the ring? Or?
Well, you do induce current in the initial state.
Yeah, but the initial state is without current.
No, because the initial state corresponds to this shifted Fermi in momentum space, so it does carry current. So the point is that the current just does not decay at all if you control
Yeah, sure.
Yeah.
If you start with
Yeah.
fermions without current and
Yeah.
you apply flux,
Right. Yeah.
would you get a current?
Yeah. Yeah.
Okay.
Yes. Okay. So of course this kind of analysis is probably justified in some sense probably, but as I will show, the actual evolution of current expectation value is rather non-trivial, and to study that, this simple theory is not sufficient.
But can I just ask?
Yeah.
So there are two corrections to these formulas.
Mhm.
So there are the irrelevant operators in Lagrangian you have
Mhm.
discussed,
Mm-hmm.
and they are difficult to take into account. But there are also corrections to the current,
Mm-hmm.
which are easy to treat
Mm-hmm.
because it's a free theory. So the problem is, and they will introduce some dynamics,
Mhm.
but the problem is that the average comes out wrong compared to the numerics. Is that?
Your question is if I include correction to this formula,
Yeah, so
but
just,
not to.
It's infinite. It's
Mhm.
infinite power, right?
Mm-hmm.
And so we know what
Mhm,
corrections are. So they will give you dynamics.
Mm-hmm.
Yeah. And I'm just wondering.
Okay, I see. I haven't really tried, but probably that's not sufficient to recover numerical result. Maybe,
Yeah, no, no.
yeah.
I think it's not sufficient, but I was just
But,
wondering.
uh-huh.
Yeah.
Yeah, maybe we can talk later. But yeah, honest answer is that I didn't analyze this serious. Okay, so field theory approach. Okay, maybe we can do something, but it didn't look very straightforward. So we resorted to some numerical analysis. And yeah, these days you can use ITBD or IDMRG, and we just happen to use so-called ITBD. So this is infinite time evolving block definition invented by Giffre-Vidal. And basically this formulation is based on matrix product state representation of 1D quantum state. So in general, quantum state in one dimension is written like this, but then there are exponentially large number of parameters. But MPS means that you represent this set of coefficients by a product of some matrices. You can pictorize like this. Then one advantage is that actually if you use this MPS formalism, you can naturally represent the translation invariant state of infinite system directly. So there is no finite size effect. But of course, that doesn't mean that you can really get the exact result for infinite system, because these matrices need to be finite dimensional to be represented in computers. So we always introduce some sort of cutoff, which is dimension of this matrix in computer. And this introduction of finite dimension introduces some error. So basically precision is determined by this finite dimension chi. And so in practice, you want to study time evolution, then you decompose time evolution into two pieces. And at one step, you apply time evolution operators to a pair of these sides. And this u is exponential of minus ih times time step. Then you can apply this unitary operator to each pair of sides. Then the resulting state you again represent in terms of new matrix product state, and you repeat this kind of process. So at next step, you apply unitary time evolution operator to this pair and this pair. So in a staggered way, then you can approximate the time evolution way. Yeah.
In previous results, you said that you have to impose periodic boundary conditions, right? And in this problem,
yeah, actually in this calculation, actually, it's not really periodic boundary
so you
condition.
can have a
Just-
different phase
yeah.
at different edges of
Yeah.
the system in principle,
Right, yeah,
right?
yeah.
So the current doesn't need to be conserved.
Yeah, so this somehow deals directly with infinite system, but you can think this as a limit of
Yeah, no, that says that the current doesn't need to be conserved in this.
Yes. Okay. Then okay, so there are various sources of error. So first is you do some Trotta decomposition of unitary time evolution operator. That's also source of error. But the most serious one is, as I said, because you can only use finite dimensional matrix. So that is a major source of error. And people have used this formalism to study quantum dynamics in 1D. And basically, what you find is that as long as you always use finite dimensional matrix, then if you do time evolution simulation, then this approximation breaks down at some finite time. And when it breaks down depends on this matrix dimension chi. And so you can check the accuracy by doing the same calculation using the different values of matrix dimension. And then you can check how far you can trust the result on time evolution.
Can I just, so before we get to this, entanglement entropy, so we grow linearly in time supposedly, but I'm wondering about the coefficient, because it's a very peculiar initial state. So does it grow generic, I mean fast, or is it particularly slow?
No, okay, so I didn't prepare that entanglement slide, but no, it was similar to other type of, if I understand correctly. Okay. Yeah. So not particularly easy or difficult for numerical.
No, I was wondering, it's a very peculiar initial state.
I don't think so. Maybe I can check again. So this is just a sample calculation. So delta is minus 0.8. So delta is defined such that the negative value means anti-fermagnetic XXE or repulsive interaction. And the initial value of theta was pi half. Then, so this is for several different values of matrix dimension chi, 200, 400, up to 1000. But let's say up to t equals to 13 or something, all the results basically agree. So at least up to this t, the result always. And the vertical axis is just expectation value of the total current, uniform part of current. So it oscillates like this, and up to here all the results agree. But beyond t equals to 13 or something, this chi equals to 200 result deviates from other ones. So that means that this chi equals to 200 calculation is only valid up to around this point, and so on. So comparing these four data, for example, maybe the largest chi result holds maybe up to t equals to 20 or something like that.
Which is quite large, by the way.
Yeah.
So I think entanglement entropy does grow quite slowly here. I mean, 20 is very large.
Yeah, but maybe it also depends on the quantity, what quantity you are looking at. Maybe this current is maybe relatively stable quantity or something like that.
And what is the scale for time? What is?
This is basically measured in unit of exchange coupling, inverse exchange coupling. So XY interaction has coefficient 1. So that determines the time scale.
Did you measure average kinetic and interaction energies actually after the thing? And how does it change this time?
You mean expectation value of exchange energy?
Yeah.
The average energy should be conserved, right?
Yeah, but it separates terms, kinetic and...
Oh, kinetic and interaction. Yeah, it should have been measured, but sorry, I don't have the data now.
So can I, if you do the free fermionic case, do you see that the current is conserved?
Yeah. Maybe later I will show some of the data. So this is for, of course, for interacting. Okay, so in that way, we can at least roughly know up to what time we can trust our result. And so this is a result for various different values of the delta, minus 0.1, 0.1, minus 0.3, 0.3, minus 0.5, 0.5, and so on. So you can see that at t equals 0, just after the quench, there is always non-zero value of the uniform current because your initial state has shifted, momentum boosted Fermi C or something like that. Then with the time evolution, it starts decaying. But so this is for relatively large value of initial flux. Then it starts actually oscillating. Then it approaches apparently to some stationary value. And so for this large value of initial flux, basically oscillation, some sort of oscillation is visible for any value of anisotropy or interaction parameter. And so it's not easy to accurately estimate stationary value, asymptotic value of current, but you can roughly guess what kind of value you expect. And what is interesting is that for large negative value of delta, like minus 1.5, minus 1.2, minus 2.0, the current decays with oscillation, but it's apparently converges to 0. So the asymptotic value of the current or stationary value of current is 0 if delta is smaller than minus 1. That is, if you are in the nail phase in XXZ language. But in the gapless phase, delta between minus 1 and 1, it seems like the asymptotic value of the current is non-zero.
So, Masaki,
Yeah.
it's really difficult to say, looking at that it's not going to go to C.
Right, yeah. But, well, yeah, so how to extrapolate this is kind of tricky question. But for this one, yeah, we can see it's almost 0. Yeah.
Can I ask, so this is all at half filling, supposedly, is that?
Yes.
And
Yeah.
did you also study other fillings?
Not so much at the moment.
And this was independent on the flux you had. This was independent on the flux you had.
Independent of.
Imagine you fix J, this is delta, and then you change the flux. So if you increase flux, would you also get this transition? No, not transition, but.
You mean?
Theta naught. He asked about theta naught.
Yeah. So if you change theta naught.
Oh, I'm coming to different one. So this is for relatively large value of initial flux.
I have another question.
Yeah.
Even before you say that for like once you have the ferromagnet, it's irrelevant whether you have a quench of the or you have the pulse or not. I mean, it's empty or
Right.
full, right? So
Right.
why is it that you have dynamics?
No. So sorry. This delta negative. So maybe it's unconventional, conventional. But this is in nail phase, anti-permanent. So the ground state is still non-trivial.
Oh.
Yeah. So if you have delta equals to, let's say, plus 2.0, then it's ferromagnetic field. Then it's trivial. Yeah. But this is anti-ferromagnetic phase, so it's.
Just one more question.
Yeah.
So here we see that plus minus delta and converge to similar value. Are they supposed to be the same? Or
Yeah, I'm coming to that point. Yeah, that's the important point. Yes. So this is basically a similar calculation for initial value of the flux or vector potential at each link, just 10% of pi, so relatively small. Then, yeah, for these values, there is no oscillation, at least no visible oscillation. They converge quickly to stationary value, apparently. But for strongly anti-ferromagnetic or repulsive interaction, there is still some oscillation. But the fact that the asymptotic value seems to be 0 in the gapped phase is unchanged. But actual behavior is kind of different. So anyway, if you compare similar value of delta, for example, plus 0.8 and minus 0.8, for repulsive interaction, the current decays strongly. And for attractive interaction, the current decays little bit, but not much. So there is a difference between negative delta and positive delta. Okay, and so this is not infinitesimally small, but relatively small. And then the natural question is, what happens if this initial value of theta is very, very small? For infinitesimal value of initial value of theta, which corresponds to delta function like pulse of electric field, but with very small amplitude, then you can expect that then linear response theory should work. So in that limit, actually, the asymptotic value of the current or stationary value of current is related to so-called Drude weight. So Drude weight times this amplitude of delta function electric pulse is nothing but the asymptotic value of the current. So usually Drude weight is defined in frequency space. So the conductivity you decompose as delta function plus regular part, and the Drude weight is a coefficient of the delta function of AC conductivity. But if you fully transform, you can find this relation. And at least, so at t equals 0, there is actually simple formula for Drude weight, which is obtained exactly from Bethe-Ansatz, which is well-known result. And as you asked, actually, if you plot the Drude weight as a function of anisotropy interaction parameter delta, actually it's symmetric, should be symmetric like this. And also, this Drude weight is at zero temperature is naturally non-zero only in the gapless phase, and in the gapped phase, this Drude weight is 0. So this is known stuff, and if I, before comparing to the numerical result, you might wonder if GG can be applied to this problem.
Sorry, can I?
Yeah.
So, but my question was for,
yeah.
So this was linear response result, so where you get the same value of D for get the minus delta, but in previous slides you had
I'm coming to that point.
Right.
Sorry, maybe I should send this slide later, but so before making comparison, so you might ask about GG. So actually there is a recent paper by these people, including Prof, that they pointed out that if you apply usual or standard GG based on local conserved charges, then expectation value of the current is 0 in that kind of GG. So that means that, if you believe in linear response theory or in our numerical calculation, in the gapless phase, the asymptotic value of the current is non-zero. So that stationary state has non-zero current. And then that cannot be described by this standard GG at least. And then they discussed, so of course Prof has this very interesting quasi-local conserved charge, and they discuss if you include those quasi-local charges in construction GG, then maybe you can describe this current carrying stationary state as a GG, but you cannot just using the local conserved charges. That's their comment. So going back to the comparison between numerical results and this Drude weight business. So as I mentioned, numerically actually, okay, so first point is that asymptotic value of the current at time infinity, numerically we find that it's apparently 0 in the gapped phase, but it's going to some non-zero value, at least if I naively extrapolate. It's a bit tricky business, but at least for these values, it seems to go to non-zero value. So at least naively from numerical results, the asymptotic value of the current is non-zero in the gapless phase and 0 in the gapped phase. And this is actually consistent with linear response theory plus exact Drude weight, because Drude weight is non-zero only in the gapless phase. So that is okay. But then So Drude weight, according to exact calculation, should be symmetric between positive and negative delta, but the numerical result is clearly asymmetric between, let's say, plus 0.8 and minus 0.8. So numerically what we find is decay of the current is actually larger for negative delta, which is repulsive interaction or anti-fermionic interaction in our convention, compared to attractive interaction.
But this is not surprising, no? Because Drude weight is a property of the spectrum in the end of the day. The spectrum is symmetric between delta and minus delta. But this is not a property of the spectrum, so why should...
Well, but still, for infinitesimal pulse,
because then it's a property of the spectrum.
Yeah. But this is maybe relatively small, but still finite. Yeah, that's the So what we found basically is that there is some sort of non-linearity, which is probably not surprising. Okay, so if you plot this, so this is comparison between linear response theory versus numerical value we extrapolated, so asymptotic value of the current. So we just took the ratio between asymptotic value of the current to Drude weight, and plotted as a function of this initial value of the flux, which gives you the amplitude of the delta function electric pulse. Then if linear response theory is exact for finite amplitude pulse, then I should expect this straight line, black line. And then we plotted what we actually obtained like this. Then you find that for positive delta, which is attractive interaction or ferromagnetic interaction, of course there is some deviation, which is not surprising, but the result quickly converges to linear response theory expectation. But for repulsive interaction or anti-ferromagnetic interaction, there is strong deviation. So, well, of course, for really infinitesimal pulse, I expect they converge to linear response theory, and even in this plot, there is some tendency to recover, so converge to linear response theory, but only for very weak pulse. And for finite amplitude pulse, there is a rather strong deviation, and this deviation. So the conclusion is that the nonlinearity is not symmetric, although Drude weight is symmetric, but nonlinearity is stronger for. This should read repulsive interaction. Sorry. Yeah.
Would you expect to restore the symmetry for small thetas if you switch on the potential adiabatically slowly?
Oh, yeah. So this is sudden quench, but if you
I'm trying to understand what comes from finiteness of theta into this comparison with Drude weight. As it's just finiteness of theta, or the fact that you don't switch it adiabatically.
Oh, okay. Yeah, that's a good question. Yeah, I don't know the answer. Yeah, maybe both. Yeah, actually, this was also pointed out by some other group a little bit earlier. So they studied similar quantity, and I think their definition of delta is negative of ours. But they also extracted Drude weight corresponding quantity from finite time calculation, and for delta negative, that means that corresponds to our delta positive. This is attractive interaction regime. Then linear Drude weight linear response theory is very well reproduced, but if you go to repulsive interaction, then deviation is stronger. Okay, and so we can also plot the deviation from linear response theory. So this is 1 minus asymptotic value of current divided by d times theta 0. So if linear response theory is valid, then this should go to 0. And indeed, for attractive interaction, it quickly decreases as you decrease theta 0. So this is log scale, so this is pretty small. But for repulsive interaction, it doesn't converge very quickly, but it seems to decrease slowly. So eventually, the deviation is expected to go to 0, but rather slowly. But as you have seen, this comparison is based on the extrapolation. So estimation of the asymptotic value is kind of tricky because we only have finite time data up to t equals to several order of t equals to 10 or something. And for example, if I fit actual data with this simple constant plus some decaying oscillation, then okay, sometimes we can fit reasonably, but fitting is not very good. So estimation is actually tricky. But still, the deviation from linear response theory seems to be real. For example, if I take delta equals to 0.5, the actual data is like this, and delta equals to minus 0.5, actual data is like this. And if you apply linear response theory and the exact value of Drude weight, prediction is here. So whatever extrapolation you do, they are well below this linear response theory result. So the nonlinearity is real, although exact amount is a bit hard to determine, but there must be some nonlinearity. I'm sure. Yeah.
You're using exponential fit. So is that better than power law? I mean.
Yeah. So yeah, I think it depends. For example, in this region, its decay is pretty quick. So
Yeah, I know that. Yeah.
So in this region, it's not clear which is better. Okay. Then another interesting feature is this oscillatory behavior. It approaches to stationary value, but with some oscillation. Then we can extract the frequency of this oscillation by some fitting. Again, this is a bit tricky fitting, but we can still estimate frequency. Then we have plotted this oscillation frequency as a function of interaction parameter delta. Then at delta equals 0, the current is completely constant, and there is also no oscillation, or this frequency goes to 0 in the limit of non-interacting free fermion case. But then numerically what we found is that basically this oscillation frequency is proportional to the absolute value of delta. So the nonlinearity is asymmetric, but this frequency itself seems pretty symmetric, although not completely. And also this oscillation frequency depends on the initial value of the flux, which gives you the amplitude of the electric flux. And another interesting feature maybe is that as long as this frequency is constant, so delta equals to -1 corresponds to phase transition point between gapless phase and gapped phase. But this frequency seems to be insensitive to this phase transition. It just continue growing to larger value if you cross the phase boundary. And we don't really have good understanding about this result, but if I extend this equation of motion approach, then the second derivative of the current, uniform part of the current is given by this double commutator. And I get a lot of complicated terms. But if I forget about these complicated terms without any justification, then the first term actually gives a harmonic oscillation of the uniform part of the current. And from here, you can read off of course, the frequency that is just absolute value of interaction delta divided by 2. But this simple argument doesn't give you theta dependence. So this is, of course, not really precise, but maybe this dependence on delta may be understood partly in this way, but this is just argument. So next, I want to discuss where this oscillation comes from. And as I said earlier, this current is written in terms of momentum occupation number like this. So if you have asymmetric distribution in momentum between positive k and minus negative k, then you get non-zero value of the current. Then also, as I said, in the initial state, you have ground state, which is basically momentum boosted of ground state at zero flux. So one natural expectation is that you have some momentum distribution. Then in initial state, you have shifted distribution. Then maybe this momentum distribution function oscillates as a whole. That is, this momentum boost may oscillate. Then you can expect, if that is the case, then you can expect oscillation in the uniform part of the current. But when we actually looked into this momentum distribution function, then this oscillation does happen, but the amplitude is rather small. So this is not very clear, but this is for initial value of flux pi 6, the delta equals to 0.5 attractive interaction. Then red points are at 0 time, just after the quench. And then for t equals to 7.5 and 15, it's almost the same, but there is slight shift of momentum distribution function, which gives some oscillation, but the amplitude is not so big. So actually, most of the oscillations, which is clearly visible, which I have shown in several slides, actually do not come from this entire shift of momentum distribution function. Instead, what happens when I see significant oscillation in the current is like this. So this is a momentum distribution function for initial value of flux pi third, and the repulsive interaction delta equals to minus 0.5. Then you see the oscillation of current like this. Then in this case, what actually happens in the momentum distribution function is not like this horizontal shift, but rather you find the formation of the dip in the momentum distribution function at some particular momentum. And also there is a new peak appearing in the momentum distribution function at some particular momentum. So initial state is given by this red curve, which is just shifted momentum boosted ground state. Then as time goes on, after time evolution, you find a dip in the momentum distribution function and this peak. And this dip and peak is what this basically contributes to the oscillation of the current. And
the difference between the dip and the peak is high?
Yeah, they are related by pi. But I don't really understand why this occurs, but numerical observation is that this dip and peak are basically responsible for this oscillation of current.
But the dip and peak, so do you know the theta not dependence?
Yeah, so I'm coming to, So it's like this dip momentum and peak momentum is just shifted by pi. So we just need to know this dip momentum. And it seems to depend roughly linearly on this amplitude of the pulse or initial value of the vector potential. So it's roughly linear, and there is some weak dependence on this interaction parameter. But again, I don't know what is determining this. Okay. So we have some maybe interesting numerical observations, but largely I don't really understand why those are the case. So maybe you can give me a better idea. Anyway, to summarize, so we studied this particular case of quench in XXD chain or spinless fermion chain, and the flux quench is equivalent to application of data function electric pulse. then the asymptotic value after long time after the quench should correspond to Drude weight if we apply linear response theory. And in fact, I believe that in the limit of weak pulse, the result should converge to linear response theory result. But for small but finite value of amplitude of the electric pulse, actually we find rather strong nonlinearity, especially for repulsive interaction regime. So for attractive interaction, the linear response theory works pretty well up to rather big amplitude. Yeah, so actual evolution is not symmetric in delta to minus delta, although Drude weight is symmetric under the change of the sign of interaction. So as I said, for repulsive interaction, we find strong nonlinearity, actually, which means stronger suppression of the current. And intuitively, this is sort of natural, I guess, because even in the gapless phase, we have tonal Rattinger rigid phase, but the Rattinger parameter is changing continuously. And very intuitively speaking, for attractive interaction, this tonal Rattinger rigid is closer to superfluid. So superfluid off-diagonal correlation function decays more slowly. But if you go to repulsive interaction regime, you have more like a charge density wave. Although in 1D, both CDW and superfluid order is not really long range, but there is quasi long range order, and there is a different tendency between repulsive interaction and attractive interaction. And for repulsive interaction, system is more like charge density wave. So it's natural, I think, to have stronger suppression of current. But at this point, the argument remains rather hand-wavy. Also, we find some oscillation in the total current in the approach to asymptotic value. And this oscillation frequency is roughly proportional to the absolute value of interaction, but also depends on this initial value of the flux or amplitude of the electric pulse. And this oscillation can be attributed to dip and peak in the momentum distribution function, but we don't know yet exactly how this appears. So yeah, I would appreciate your suggestion or input. Thanks for your attention.
Well, thank you very much. So we've had a few questions already, but we have time, Sasha.
So this oscillation, so there is a dip and peak developing, and then they kill itself. It's like backward.
Yeah. So the oscillation eventually dies out. So it keeps oscillating for a few times maybe, and then.
But then the whole distribution shifts.
Oh yeah. Good point. Oh, maybe, okay, yeah. Maybe I forgot to include that slide. But yes, eventually, yeah, this peak merges with this original distribution, and this dip kills this part of the distribution, but not completely, yeah. So, yeah, sorry, maybe I can show you later that part. But because the stationary state after infinite time has non-vanishing current, the distribution does not completely move back to the original one. But it does reduce some current compared to this initial state shown in red.
Yeah, so my question is, so there's this a special point delta is -1.
Yeah.
Do you have any statements about this point? Because the transport is normally anomalous there in the linear regime. So do you have any statements about this nonlinear response?
Yeah. Oops. Sorry. So.
Do you see some critical?
Yeah. I know what you mean, but probably, yeah, I think probably there is some anomaly at delta equals to -1 at antiferromagnetic point, but in this calculation, the precision is not enough to see that sort of subtle singularity. So what we could see is just that roughly at this antiferromagnetic XXZ point, XXX point, just the asymptotic value just goes to 0. Beyond this point, the asymptotic value is clearly 0. And before this point, in the gapless phase, asymptotic value seems non-zero. So this value does seem to be at the boundary between this behavior, but probably, yeah, there is some logarithmic or whatever, some peculiar behavior at this point, but within this calculation, it's hard to see.
Is there a regime which corresponds to continuum limit, actually, or you need to do it adiabatically in this case? Yeah.
So
I was just asking if there is some regime which could correspond to a continuum limit, or you always have to switch this perturbation adiabatically for this case. And what would you expect?
What was the question?
About adiabatic.
yeah, so in
Not adiabatic, but continuum limit of it, because he studies system analysis, right? So
yeah, the question is, we studied delta function like electric pulse, but you can elongate. Yeah, I don't know exactly. But if the amplitude is weak, then we are supposed to apply linear response theory either case. So the difference vanishes, I guess, in that limit. But for finite amplitude, yes, that's. So maybe you can kill this oscillation. And intuitively, I expect that if you don't apply delta function pulse, but rather some pulse with finite time width, then
it looks like
probably you can
It's the
kill
usual
it.
for quenches,
Yeah.
right? I mean, so
Yeah.
if you look at times late enough compared to your pulse time, I mean, so it looks like a quench. Yeah. I mean, I think this is generic.
Yeah.
So there was Marcos, yeah.
So just this issue of the long time and I mean, being convinced that one can properly extrapolate. I mean, have you checked if you add non-integrability, your fitting procedure always give you zero current?
Oh,
Good point. Yeah.
that's good point. Not really. Maybe I should. Yeah.
Austin, do you have a question? Sorry.
What's the luck?
Okay. Are there any other questions? No. Okay.
Is it possible to treat disorder, actually? Many people studied disorder in rings, so I don't know if Diamargy can...
Well, so the calculation becomes obviously harder because here we assume translation invariant state, then you just need to use one matrix. So in principle, you can introduce some disorder, then you need to use a different matrix to represent, so product of different matrix depending
Is it
on.
doable with this current techniques?
I'm not expert, but yeah, some people are studying disordered system using Diamargy, so probably it can be done, but I don't remember any work on quantum dynamics with randomness using this kind of approach, so I'm not sure, but maybe some experts can do that.
Okay, let's thank Masaki again for a very interesting talk.